The last lesson before our midterm will be on Earth's interior, the layers of the Earth. The Earth, as it cooled, formed layers. These layers move from most dense toward the center to least dense toward the crust. So you get a temperature increase and a density increase as you move in toward the core. The continental crust, which is the least dense of our crustal features, is made of highly quartz rocks. We refer to these rocks as granitic. We have found rocks as old as 3.8 billion years old on the continents. So this is the oldest rock layer. Oceanic crust is slightly more dense. It contains less quartz and more of the metallic minerals. It is young relatively because of the ocean's conveyor belt, subduction occurring at the margins, and the creation of new crust at the mid-ocean ridges. So the oceanic crust is slightly more dense, and we term the rocks basaltic. The Moho, or Mohorovic discontinuity, is the thin boundary between the crust and the mantle, which is a phase transition from the rigid crust to the amorphous, solid, but plasticky mantle. In the mantle, you have convection, hotter toward the core, streaming up, cooling, and then sinking down. This is what powers our plate tectonics. The asthenosphere is the upper layer of the mantle. And of course, that mantle convection is illustrated in this image here. The mantle is the most voluminous portion of Earth's interior. The outer core and inner core are made mostly of iron and nickel metals. The outer core is a liquid, but pressure increases as you move deeper, and the pressure forms that liquid metal to a solid for the inner core. The spinning of the Earth and that liquid solid metal conglomerate in the core is actually why we have a magnetic field, which is important because magnetic field blocks us from solar wind. This is a summary of our crust and layers underneath. We study seismic waves, and the seismic waves tell us about the inner Earth. We know that waves change speed and are bent as they move from one media to another because of density differences. So we can use that information to extrapolate data and hypothesize what the inner Earth is like without actually seeing the inner Earth. So P waves are bent when they pass to the core, and we use this data to determine where the core is. Waves cannot pass through a liquid, so we know that it's a liquid because of the S-wave shadow zone.